Hi, Toastmasters. Today, I'd like to give a speech about an interesting concept in engineering that I think is super insightful and super enlightening. But I promise there's no equations, there's no complicated math. I've tried to make it as practical and understandable as possible. So here goes. I think everyone's familiar with the basic concept of averaging. The concept of average is just you take a bunch of numbers that you've sampled, you sum them up, and you divide by the number of samples. This is the only equation in the entire presentation. And the main application of this, we can imagine we have a sample set of noisy data. So we might be sampling the temperature on a given day, or let's say the number of voters who voted in certain counties for certain candidates. And we just average all of their votes or average the temperature to get one clean, simple value like 0.5 is the average. There's another visual representation of this where in something like long exposure photography, you have the shutter of a camera open for a long time. And the resulting photograph is essentially an average of all the little frames that you would have taken at every single time step between the shutter opening and the shutter closing. So on a pool table with a stack of pool balls that are fixed and a few that are moving around, when you average them out, you see that the ones that are moving around get faded into the background, and the ones that are stationary, as well as the table and the floor and everything else that's stationary, is amplified in contrast. And another picture on the right, this is of a square in Germany where you can see the people who are moving back and forth because their movements are faster than the shutter speed because it's open and closing, it's open and open, left open for such a long time. The people's movements are averaged out as little dim fades, but the buildings and the stone in the ground is left constant. Now, I want to flip the story a little bit because I've talked about how we can average existing information to generate less noisy information. But let's flip the story and understand how we can use averaging to generate precise information from imprecise guesses. So what do I mean by this? Let's say we have an ice cream shop and we want to survey customer ratings of our shop on a scale of 0 to 1. We want to understand exactly where on that scale we fall into as an ice cream shop so we can understand how we compare against our competitors. But the problem we have is our customer ratings are very imprecise. Whenever they come to our store, they either love it, meaning they rate it a 1, or they hate it, meaning they rate it a 0. So how can we actually understand the true rating we have on a scale of 0 to 1? Well, here's a simple way we can do it. We can take many samples of our customers, and then we can average all of these ratings overall to get a preciser measurement of the rating for our store. So if we only took one sample, that rating is only going to be 0 or 1, meaning the average is also only going to be 0 or 1, which is pretty imprecise. If we take two samples, the average can now take on three values, 0, 0.5, or 1. And if we take three samples, we can have four different values, 0, 1/3, 2/3, or 1. So with every amount of increased sampling we do, the average rating itself becomes more precise, despite the fact that the customer themselves is an imprecise rater of our store. So sampling more and more lets us use an imprecise rating score to generate a precise score for ourselves. That's what I want to convey here. But this might seem kind of inefficient because we have to ask the same customer many times to rate our store while they're in the same mood. So let's say their mood switches every 10 minutes. We have to make sure we ask them 3 times within that same frame of 10 minutes. And that can get a little impractical in a lot of engineering situations. So can we do better than this? The answer is yes. And the answer itself is very cool. So to explain this answer, let me pose a dictionary problem for everyone here. Let's say we have a dictionary, and it's a pretty thick dictionary. It measures 3.49 inches in thickness. But let's say we have a super imprecise ruler. Our ruler can only measure 0 inches or 6 inches. It has no tick marks in between. So we, as a human, have no way of using this ruler to measure 3.49 inches. All we can do is measure 0 or 6 inches. Can we somehow use this imprecise ruler to still precisely measure the dictionary height? The previous method I showed you would say, just keep averaging the ruler over and over again. And if the ruler is a little bit noisy, like if sometimes the measurements get corrupted, maybe over time we'd converge to 3.49 inches. But let's say we can do even better than that. Here's what I'm proposing. Let's use our previous guesses of the dictionary's height to inform our future guesses. So what we're going to do is we're going to take the ruler, we're going to put the dictionary next to it, and every single time the top of the dictionary crosses a tick mark on the ruler, meaning either the 0-inch mark or the 6-inch mark, we're going to record our guess as 6 inches. If it doesn't cross any tick marks, we're going to record just 0 inches. So the first time it crossed the 0-inch mark because it's clearly more than 0 inches tall. So we're going to record 6 as our first guess. We then stack another dictionary on top and we repeat the same process. So 3.49 plus 3.49 is more than 6 inches. So it crossed the next 6-inch mark and we record another 6. We do this again. We stack a third dictionary. Now we need to add another ruler, but let's pretend it's one long ruler with intervals of 6 inches. This third dictionary doesn't cross another 6-inch mark. So we record a 0 for this third measurement. And we take the average of all of these measurements. So let me give a block diagram of the way this looks. And this is a bit complicated, so I'll walk through this step by step. On the left side, we have our actual input signal, quote unquote, which is the precise value of the thickness of our dictionary, which is 3.49 inches. We take this signal and we enter into this feedback loop. So let's walk through this feedback loop step by step. At every point in this feedback loop, we have an accumulator that accumulates the error of all of our past guesses. The output of this accumulator is then fed to a decision boundary where if it's above a certain level, in this case a tick mark, we say the output of this decision boundary is 6 inches. If it's below that, we say it's 0 inches. We then store our previous guess and we subtract that guess from the input, which is 3.49 inches, to then feed into our accumulator. And this repeats over and over again for every iteration of this process until we eventually take the average of all of those decision outputs and we average them to get what we think is the dictionary thickness. So I didn't just make up this technique. This is called delta sigma modulation. And the basis of this technique is that we use the error from our past guesses to inform our future guesses. And you might be asking, why is it called delta sigma? It looks kind of fancy. There's Greek letters involved. The reason is because the delta comes from the fact that we're taking the difference of our past guesses and the actual value. And the sigma comes from the fact that we're accumulating or summing the errors of all of our past guesses to inform our future decision boundary. That's why it's called delta sigma modulation. And let's look at what this actually does. So I've written a little Python script here to simulate what this might look like over 50 iterations. And what you see here in blue are the guesses of our measurements. So our guesses are only 0 or 6. There's nothing in between. The red dashed line is the actual thickness of our dictionary. And you can see that over 50 iterations, the green line, which is the average value of all of our guesses, nicely converges to something around 3.49 inches. It still fluctuates a little bit, but you can see that the fluctuations get a lot smaller over time. So with just a super noisy or imprecise ruler, we've been able to extract really precise measurements by sampling it many, many times in this clever way of using our past guesses to inform our future ones. Now, the key here is that the dictionary height itself is not changing while we're stacking dictionaries on top of each other. Let's say one dictionary was a certain height, then we stack another one, now the height changes. That would completely corrupt this entire system. So the key flaw in the system, if you will, is that the measurement we're trying to measure, that item, has to stay constant over the course of these measurements. So we're essentially sampling something that looks to us as static, even though we're sampling it many, many times over time. But it's a pretty cool concept and it lets us make very precise measurements. This is another way of looking at the same problem. Let's use this delta sigma technique to generate precise quantities. So far we've only been measuring things, but now let's generate precise things. So let's say we go to a coffee shop. The barista tells us it's $2.31. I've never paid something like that in over 10 years, but let's pretend for the sake of this example that it only costs $2.31. But let's say we have a conundrum, which is their credit card machine is broken and they don't have any change. And all we can pay is in $5 bills. We have no other types of change, only $5 bills. So here's what we'll do. We'll tell the barista, if the remaining cost that we owe you exceeds $2.50, we'll give you a $5 bill. If it doesn't exceed $2.50, we're not going to pay you anything. And when I say residual cost, I mean, every time we pay them $5, they're going to subtract that from the amount that we owe them to inform our future debt, basically. So you can see that in this Python script I've written again, the blue lines are the payments we make. So sometimes we pay them $5, sometimes we don't. And we kind of do this in a periodic fashion, on, off, on, off. And over time, the average payment we pay the barista actually approaches exactly $2.50. So we can use delta sigma modulation not only to measure precise quantities, but also generate precise quantities. In this case, we're generating a payment that's quite precise. So these are all kind of toy examples, but this technique is actually very powerful and used widely across a lot of electronic equipment. If we want to talk about recording or measuring things, this technique is actually used very often in audio recording equipment, also in biomedical devices like ECG monitors, and also precision temperature sensors. For generation, like the other side of this, audio synthesizers use this technique. And the reason audio shows up in both sides is because the human ear is actually very perceptive to noise or distortion in sounds. So it requires very high fidelity or high precision sensor and generator to generate and measure these signals. It's also used in radio frequency synthesizers. And this is pretty cool because let's say you have a car radio that hops between different radio stations. And normally car radio stations are spaced at 200 kilohertz. You might have like 99.7 FM or 99.5 FM. But let's say you want to generate a station at 99.567 FM, something really, really precisely. What you can do is you can hop between those two adjacent stations in a very cleverly timed way, such that the average frequency you generate is at that precise frequency you've come up with. And also in electronic measurement equipment and generation equipment in labs. And the key here is that all of these rely on relatively slow moving or static underlying signals that we can quickly measure or generate imprecisely to produce an average value that's quite precise and quite much a replica of what we're trying to measure or generate. So I packed a lot of information into this, but hopefully there weren't too many equations or symbols that overwhelmed everybody. I think it's quite amazing to see what averaging in this clever fashion can do for us in terms of measuring things precisely and generating things precisely. And it's a quite magical thing to think about when you first learn about it, which is how I felt. And I hope all of you shared that same level of excitement about this technique. Thanks.